Welcome to the Explainer. You know, in materials science, there's this weird paradox. Sometimes, when you try to make something better, you actually end up making it way, way more complicated. Today, we're going to dig right into one of those fascinating challenges. So, here's the big question, right? How do you make a steel part, say a gear, incredibly tough on the outside so it doesn't wear out, but you keep its core strong and resilient so it doesn't just shatter? This is a huge challenge in engineering, and the classic answer is something called case hardening. Okay, so here's the game plan. We're going to start with that basic quest for hardness, then look at the traditional carbon-only way of doing things. After that, we'll introduce the hybrid method, carbonitriding, and see how that shakes everything up. It creates a massive measurement problem, one that even AI struggles with. And that's going to lead us to what we're calling a new hybrid mindset. All right, section one, the quest for hardness. So what are we trying to do here? Well, the goal sounds simple enough. We need to create a super hard, wear-resistant outer layer, that's the case, on parts like gears and shafts. But, and this is crucial, we can't make the whole thing brittle. It still needs to have some give. Okay, so let's get into the classic solution. This is the baseline, the carbon-only approach, which is all about a process called carburizing. For like 100 years, this has been the standard. So what is carburizing? Well, the idea is pretty straightforward, actually. You take a low-carbon steel part, you heat it up in an atmosphere that's just packed with carbon, and those little carbon atoms, they just soak right into the surface, kind of like a sponge, creating this gradient of carbon from the outside in. And check this out. This graph shows you exactly what happens. It's beautiful, right? On top, you've got the carbon content, and on the bottom, you've got the hardness. As you can see, as the carbon increases near the surface, the hardness follows this perfect, clear, measurable curve. It's a clean, predictable relationship. More carbon equals more hardness. Simple. You know exactly what you're getting. But, engineers are never satisfied. What if you want to make it even better? What if one element just isn't enough? Well, that's where we get to our hybrid process, carbonitriding. Okay, so carbonitriding. It's basically a modified version of what we just saw. But this time, we're throwing a second ingredient into the mix, nitrogen. We do this by adding ammonia to the furnace. And why do we do that? Well, it seriously enhances the hardenability, which is a huge deal, especially when you're working with less expensive, plain old carbon steels. So let's put these two side by side. With carburizing, you're just adding carbon. With carbonitriding, it's carbon and nitrogen. Notice the temperatures. Carbonitriding runs cooler. It also makes a shallower case. But here's the trade-off, and this is the whole point. You get this enhanced hardenability, this set of properties that carbonizing by itself just can't give you. It's a classic engineering compromise. Okay, remember that nice, clean, predictable graph from before? Well, look what happens now. With both carbon and nitrogen soaking into the surface, both at their own different rates, that simple relationship between depth and hardness just falls apart. It's complex, it's messy, it's ambiguous, it's a whole different ballgame. And this brings us to a huge problem, the measurement challenge. How in the world do you measure something that you can't easily predict? This is the paradox, right? We've made the process better, but in doing so, we've made it incredibly difficult to inspect and control with any real confidence. Yeah, that crystal clear link we saw before between the diffusion, the microstructure, and the hardness, it's just gone. It's all become murky, a much fuzzier picture. We've traded certainty for performance. Now, I love this comparison because it shows just how far our tools have come. From old-school analog microscopes to these amazing digital imaging systems, we can measure things with a precision that would have seemed like science fiction not too long ago. But here's the kicker. Having better tools doesn't solve the fundamental problem. We can get the data, sure, but what does it mean? How do you interpret this super complex data that this hybrid process spits out? So if our traditional methods are struggling, what's the next logical step in the 21st century? You guessed it. Can AI crack the case? Can machine learning find the hidden patterns that we can't see? All right, so you've got two different ways of thinking about this problem. On one hand, you have traditional tools like CalFAD. These are based on pure physics and thermodynamics. They're slow, they're heavy on the computation, but they understand the why. On the other hand, you have AI. It's lightning fast, it's all about finding patterns in data. But it doesn't really understand the physics. It's just looking for correlations, which can be risky. And that leads us to one of the biggest dangers with AI in this space, a thing called overfitting. This quote nails it. The model can get so good at explaining the specific data you trained it on that it basically just memorizes the noise. The second you show it a new, slightly different real-world situation, it completely falls apart. It hasn't learned the general physics, it's just learned the test. So yeah, AI is definitely not a magic wand here. First, you need tons and tons of high-quality data to train it, which isn't always easy to get. Then, there's that huge risk of overfitting we just talked about. Plus, there's the black box problem. A lot of the time, we don't even know how the AI is making its decisions. And because it doesn't understand physics, it can sometimes come up with predictions that are just physically impossible. For critical parts, that's a risk you just can't take. So where does that leave us? This is where it gets really interesting. It brings us to a new way of thinking. The process itself is hybrid, right? Carbon and nitrogen. So what if our thinking needs to be hybrid too? What if we need to combine the best of both worlds? And this is what that looks like. It's a three-step dance. First, you start with the physics. You use those traditional simulation tools to create a solid, physically accurate baseline. You generate good, clean data. Step 2, now you bring in the AI. You train your machine learning model on that high-quality simulated data. This lets the AI explore all the possibilities super fast, but within the guardrails of real physics. And finally, step 3, you bring it back to reality. You run a few very targeted real-world experiments to check the AI's predictions and fine-tune the model. You keep it honest. This synergy, this dance between simulation, machine learning, and real-world experimentation, that's what we're calling hybrid thinking. It's not about pitting physics against AI or humans against machines. It's about creating a powerful partnership where each one makes the other better. And this brings us to the final big idea. As our technology creates more and more of these complex hybrid systems, is the future really about pure automation? Or is it more about mastering this art of hybrid thinking? I mean, this goes way beyond just treating steel. It suggests that as our world gets more complicated, the best solutions won't come from just computers or just people. They'll come from blending the incredible power of computation with deep, irreplaceable human expertise.